Good morning from Dhaka, Bangladesh. This is the 9th lecture of AS and A-level chemistry lecture series. And the 8th lectures we finished. There we had problems on empirical formula. The next slide, we have more problems on molecular formula. And molecular formula of a compound shows the number of atoms of each element present in the body. How to find out molecular formula from a given data? You see, an empirical formula is given, and then the relative molecular mass is given. We are asked to deduce the molecular formula of this compound. What else is given? Relative atomic masses of bromine, carbon, and hydrogen. Why? Here you see in empirical formula, we have carbon, hydrogen, and bromine. That's why relative atomic mass of carbon, hydrogen, and bromine is given. What is to do? Find the empirical formula mass of CH2Br. And it is easy from this data. From this data, we can find it out. And it comes out to be 93.9. What we have to do now? We have to divide the molecular mass by empirical formula mass. Molecular mass is given here, and the empirical formula mass, we find it out, and then we get 2. Ratio is 2. Then multiply this 2 with the empirical formula. Then we get C2H4Br. So C2H4Br is the molecular formula of this compound from this data. Similarly, we can get another set of data. The empirical formula and relative molecular mass of 3 compounds, A, B, C, are given. The empirical formula, the A is this, B is this, and C is this. We have also relative molecular mass from A, B, and C. You can easily calculate now, because we know that here 3 compounds, each compound has got carbon, hydrogen, or carbon, chlorine, or carbon, hydrogen. So here is the relative atomic masses of carbon, chlorine, and hydrogen. This is given to you. So find out the empirical formula mass as we did earlier. A empirical formula mass is 41, B empirical formula mass is 118.5, and C empirical mass is 40. So now we take the ratio of molecular mass by empirical mass of the compound A. We get 2. For compound B, we get 2. And for compound C, we get 8. So now you can find out the molecular formula of compound A. We multiply it with 2, and then it's C6H10. Compound B, multiply 2, and it is C2Cl6. And compound C, multiply by 8, and we get C8H816. This is very easy way of finding molecular formula or empirical formula from a given set of data. What we do next? There is one terminology called stoichiometry. Stoichiometry of chemical reaction. We have to know that. So if every reactant exactly react and there is no waste, we can find out the stoichiometry of chemical reaction. So what is to do for that? We have to get the balanced equation of the reaction. Balanced equation of the reaction. And balanced equation of reaction means that we know the reactant plus we know the product. And then we have to, balanced equation means we have to balance all these compounds, both left-hand side and right-hand side. And when we balance it, we get the stoichiometric ratio of this iron trioxide, carbon monoxide, iron, carbon dioxide as 1:3:2:3. We take the larger number, and the larger number is 3, 2, and 3. And these are called stoichiometric numbers of a chemical reaction. Next, we go to, in chemical reaction, we have reactant. So some reactants are termed as limiting reagents, and some are termed as excess reagents. Which one is limiting reagent? The one which is not in excess in the chemical reaction. This is limiting reagent. The one which is excess in chemical reaction, this we call excess reagent. Why we are talking about this? We are talking about this to find out the product and whether we can find out 100% product from the limiting reagent. That's what we have to seek now. In calculating reactant, which one is limiting, we first of all, as I say, we always write the balanced chemical equation and then the molar ratio of the equation. Next slide. I've taken an example to show you which one would be the limiting reagent, and we could calculate it out. What is the example? A sample of 79.8 gram of iron 3 oxide is mixed with 9.36 gram of carbon and then heated. What would be the product? Product to be, because iron 3 oxide, carbon is a reducing agent, and iron 3 oxide has been reduced, and then we get iron 3 oxide plus carbon and elemental iron and carbon dioxide gas. This is what we call chemical reaction. But I say to find out stoichiometry or to find out limiting reagents, we have to have balanced equation, and B is the balanced equation. How to calculate which one is limiting reagent and which one is excess? What do? We find out the moles of iron 3 oxide. Here you see average atomic mass is given for iron, oxygen, and 12. You need not to go for periodic table because these are generally given in the question. Okay, then you easily can find out the moles of iron reacted here. This moles of iron, and we calculate it out and find out 0.50 mole. Similarly, we go for carbon and we find out the moles of carbon, 0.78 moles of carbon. So, but from this chemical equation, we know 0.5 moles of carbon. We need how much? The molar ratio is 2:3 here. So moles of carbon should be 0.5 into 3/2, and if we calculate it, we can find out 0.75 mole of carbon. So in our question, it was 0.78 mole of carbon. If we convert it into mole, it becomes 7.78 mole of carbon. But after reaction, we can it takes 7.75 moles of carbon, and that's why carbon is in excess in the reaction. Therefore, we'll call that iron 3 oxide is the limiting reagent for this reaction. This slide, we are talking about yields and atomic economics. What is yield then? When we have a desired product, and if we get the 100% desired product, we are getting 100% yield. But unfortunately, in chemical reaction, very few chemical reaction will give you 100% yield. But many chemical reaction will give you less than 100% yield. And this is because the reactants may not be totally pure, and some product lost during the transfer when we are doing the reactions. Side reactions may happen and form other products. Reaction could be slow. These are the points for which we do not get 100% yield. 100% yield means that there is no waste. And all industrialists or applied chemists, they prefer to get 100% yield, because if they have there is losses in reaction, that also impact in environment. So therefore, everybody tries that we get 100% yield, but unfortunately, we do not get it. What about atomic economy? We call it molar mass of the desired product divided by sum of the molar masses whole product into 100. That gives us atomic economy. I'm taking a problem on yield and atom economy in the next slides. What is this? Say a modern gas fuel lime furnace produces 100 kilogram of quicklime. Quicklime formula is this calcium oxide. From what? From 1,000 kilogram of limestone. So here is the chemical formula of limestone. What is it say? That we are to find out the calcium oxide, how much calcium oxide is it. So we have given it is 500 kilogram of quicklime. Now we have to find out the percentage yield of quicklime. When we convert this limestone by calcium oxide and carbon dioxide, we have this reaction. So what we do, we find out 1 mole of calcium carbonate, 1 mole of calcium oxide, mass of 1 mole of calcium carbonate is 40.10. It is the average mole atomic mass of calcium, and then carbon, and then oxygen. We do it, and then we get the 1 mole of molar mass of calcium carbonate is equal to 100.1 gram. Similarly, we can get molar mass of calcium oxide. It is 56.1. In 1,000 kilogram of calcium carbonate gives us 56.1 gram divided by this molar mass of calcium carbonate into 1,000, and we get 560 kilogram of calcium oxide. But we have given, we produce 500 kilogram, not 560 kilogram. We should get 560 kilogram. If we would get 560 kilogram, we would have 100% yield. Since we don't get 560 kilogram, we get 500 kilogram. Therefore, yield is 500 divided by 560 into 100, and 89% yield. Similarly, we can find out the atomic economy. Here is the reaction again: titanium tetrachloride and magnesium, which gives us titanium and magnesium chloride. This is the product. We are atomic. What we are saying, that we have to find out the atomic economy of titanium. What is the atomic economy of this process? First of all, we get the molar mass of titanium, and then we get the molar mass of magnesium chloride. These are the product, is it not? So here is the molar mass of both titanium and magnesium chloride, and in total it is 238 gram per mole. Similarly, molar mass of desired product, titanium is our desired product, so it is 47.9 gram per mole. So therefore, atomic economy is 47.9 divided by 238.5 into 100. We get it 20.1%. So here we will say that the atomic economy is rather poor. So this is what is what is the atomic economy and percentage yield. So we would, in many cases, we would say that the data is given and then asking for percentage yield and atomic economy in exams or in classes. Well, this slide, we talk about significant figures. In your books, A-level books, you will see that in many problems, you are asked to give the result in significant figure. So there are rules for significant figure. What are the rules there? There are many different rules, but I will talk only about rules here, a few examples. If we have a number 526.84, this number, we have significant figure number is 5, 3 plus 2, and therefore it's 5. But then in many cases, we have to find out significant figure according to the problem given to us. In the problem, we will see which one is the least significant figure. There are maybe 3 or 4 data, and you will see which one is the least significant figure. For example, here, 2.9 gram of calcium oxide. So this is the significant figure here is 2. So when we calculate that's the number of moles of 2.9 gram of calcium oxide, what we do, 2.9 gram divided by 56.1, the result comes out to be so many figures. But we have to give the result up to the significant figure. That means we have to give the result in 2 significant figures. In this case, it is 0.516. So what we are doing, we are rounding up. You know, if it is more than 0.5, then we take it in the next bigger number. So here it is 0.051693. Therefore, if we take significant figure, it is 0.0, rounding up, it is 0.052. So 0.52, you might now ask, what about 0? 0 is not counted if it is before a figure. It is not counted. Therefore, the significant figure for this is 52. Two significant figures. Here you see, if we round it up and then we round it up, then it is 526.8. The significant figure is 4. If we round this up, we get 527. So this is significant figure 3. If we round up this, we get 53. Then it is significant figure 2. So we have to always be careful in writing significant figures, and we do not do rounding up before or in the middle of a calculation. If we do so, then it's a risk of introducing errors. After the end of the calculation, we round it up and give it the result in significant figures. Okay, then let's talk about chemical bonding and structure. This is a major chapter in chemistry for both A-level graduate student and postgraduate student. We have to know very carefully what chemical bonding means and structure means. Well, chemical bonding is definitely a force between atoms in the molecule or compounds. And then, what are the different types of force we do have when we are talking about chemical bonding? So to know this, it's very useful to know the Lewis structure of elements, compounds, molecules, and compounds. Let's talk about the Lewis structure of carbon. How to draw the Lewis structure of carbon? It's nothing, that you have to get the electronic configuration of carbon and find out the number of valence electron. In this case, you see the number of valence electron is these 2. 2s2, 2p4, so 2p2. So carbon has got valence electron 4. We have to take the symbol of carbon and then arrange this as a dot or as cross, whatever. So even some other sign people may use. So I am showing you a Lewis dot structure or cross structure of some of the elements in the periodic table. You know, hydrogen has got only 1 valence electron. So we just give 1 dot for hydrogen. Similarly, in this group, all elements has got, for example, lithium, sodium, potassium, all have got only 1 electron in valence electron. So we show it with 1 dot. Similarly, for beryllium, magnesium, those beryllium, magnesium, you will go to the electronic configuration, you will see that there are only 2 valence electrons. So there are 2 dots for calcium. Boron, there are 3 valence electrons. So we have this aluminum, 3 valence electrons, and so on and so forth. Okay, this is the noble gas. You see, here it is helium, 2 valence electron. Neon has got 8 valence electron. Argon has got 8 valence electron. And this noble gas configuration is a stable configuration. All elements, when forming compounds or molecules, they tend to go for this noble gas configuration. Okay, next slide. Here are some Lewis structure of nitrogen, chlorine, methane, ammonia. Whenever we show this means a pair of electron has been shared here, and therefore we are showing it like this. We will see there are number of pairs of electron could be shared to form chemical bonding. Now we go for the first bonding, that is ionic bonding. Here the rearrangement of valence electron is either gaining of electron or by losing of electron. When it loses electron, it gets a cation. When it gains electrons, it is a anion. There are some exceptions also for noble gas configuration. This by gaining electron or losing electron, the atoms tend to go for the noble gas electronic configuration. When it loses electron, as I said, the positive ion, that is cation, and negative ion, that is gaining electron, anions. This cation and anions has got electrostatic attraction between them. And this electrostatic attraction is called ionic bond. And sometimes it is also called electrovalent. I have given 3 examples here, or 2 examples, maybe this slide. Here, sodium has got the electronic configuration like this, and then it has got the valence electron. You see, only 1 electron. But chlorine has got 7 electrons in valence shell. So it is always a tendency of sodium ion to lose 1 electron and have a electronic configuration of noble gas, and chlorine has got a tendency to gain 1 electron and get noble gas configurations. And this cation and anion, they have got form bond, which we call electrostatic bond or electrovalent bond or ionic bond. It is the most strong bond so far we will discuss. And in the next slide, I'm talking about properties of ionic bond. With this slide, we will finish today's lecture. Generally, ionic compounds are solids at room temperature and pressure. And due to electrostatic bond, that positive ion and negative ions are together, and in 3-dimensional regular arrangement, we call it crystal, that is ionic crystal, which oppositely charged ion close to each other. Ionic compounds have high melting point, high boiling point, and also high enthalpy changes of vaporization. It takes a lot of energy to overcome the strong electrostatic attractive force. That's why it's like this. Most ionic compounds are soluble in polar solvent. That is, ionic compounds are soluble in water. We have other polar solvent too. So these attraction are called ion dipole attraction. This attraction replaces the electrostatic force between the ions, and so the ions go into solution. Ionic compounds do not conduct electricity in solid state. But if we melt this, then we can see that it conducts electricity because ions are free there. Molten and ionic compounds conduct electricity because the ions are mobile, free, and therefore it conducts electricity. In the next lecture, we'll talk about covalent bond, we'll talk about metallic bond, and so forth. We are finished with this lecture. Thank you very much.